Good morning, everybody. If we are here, it's because we believe that body-worn sensor has the potential to transform the way we assess mobility. And nevertheless, the intrinsic technological limitation, the lack of standardized procedure, the lack of robust validation of pathological population are still hindering the big jump from the lab to the real world. And today I will discuss with you some of the lessons learned, challenges and solutions by leveraging on experience within the technical validation study of the Mobilise project. As technical partners, we were asked to develop and to design methods and digital tools for assessing mobility in real-world conditions. But this is not an easy task. In fact, mobility in real world is for definition unsupervised and unstructured. And it is not an easy task for two reasons, at least. First, because the signals, which appear very regular and easy to analyze for normal gait, may exhibit very different and irregular patterns for different gait disorders and severity, as you can see here for Parkinson, chorea, and stroke. Second, when you move to the real world, gait is not straight. We have to transfer to the car, indoor, outdoor conditions, we have to walk on stairs, and the patient may need walking aids. So it starts to be clear that to move from the comfort zone of the lab to the real world, we had to face a certain number of challenges of different natures. The very first one was a problem of definition. To agree on definition is very important, and to disagree may have dramatic effect, as it happened in 1999 when a spacecraft, Climate Mars spacecraft, was lost just because one NASA team was provided the data in meter and the other team in feet, literally lost in translation. NASA lesson learned, we realized from the very beginning that we needed a common language. Therefore, we identified different aspects related to real-world mobility, and for each of those aspects, we identified those terms that needed a proper definition with the intent of building and consensus based on the expert opinion from different backgrounds, both clinical and technical. For example, what is real world? What are the peculiar characteristics of it? What is walking? How do we define stride length? What is the minimum definition for walking bout? The last question is particularly important, as you will see also in the clinical validation study, because it defines the rules for data aggregation. It was decided that a walking bout has to include at least 2 consecutive right and left strides, 5 steps in total. And walking bout can be separated by a resting period, which can be anything like stopping or any other non-walking activities. And then, for each walking bout, we could define a very complete set of digital mobility outcomes based on very clear and unambiguous definition, which is essential for enabling comparison among studies. The next challenge was about choosing the ideal device. Ideal, yes, but from which perspective? In terms of accuracy, in terms of data recordings, in terms of wearability acceptance. Technology-wise, the choice was quite easy. Based on the project requirements of providing full mobility description in daily life for 7 days, we opted for a single inertial measurement unit, including 3-axis accelerometer and 3-axis gyroscope. A much more strategic choice was about the location, which in turn influenced the attachment. There are different possibilities. You can attach the unit, the device to the torso or to the lower limb. The solution is quite accurate, but relatively invasive, or to the upper limb. For instance, a very popular solution is to attach on the wrist. But then it can be quite complicated to distinguish accurately between non-walking and walking activities. To take a decision, we designed and developed an objective methodology for the selection of the device location. So we first identified 4 different domains in the field of mobility: data capture process, concurrent validity, human factors, and wearability usability. Then for each domain and each item of the domain, we assign a weight and the scoring system, and it allowed to compare and rank different solutions, and in terms of accuracy and burden of data collection. And the results were that the best trade-off solution was a single device attached to the lower limb. So now we have a common language, we have a device. The next step is to quantify real-world working. In other words, we have to identify and implement state-of-the-art algorithms which allows us to estimate digital mobility outcomes starting from the raw sensor signals. The preliminary step was to define a structure for data standardization and storing, which is essential if you want then to share the data with the scientific community. And it is also very important in the light of developing future machine learning methods. Then these standardized data were fed into the computational pipeline. These slides provide an overview of the different blocks, from gate sequence detection, stride length estimation, identification of the eligible walking bout, and estimation of primary and digital mobility outcome. More than 80 algorithms were identified, refined, compared. It was a huge work carried out by the colleague from APFL and FAO. Now, there is another very central issue and challenge that we had to tackle. So how to validate those measures. At the time we started the project, we could not find any appropriate validation framework specifically conceived for digital mobility. Therefore, we proposed and adapted this 3-level validation, including device testing, algorithm and validation using in-lab and 2.5 hours free living recordings, and 7 days real-world for acceptability. We consider different cohorts, including ultra-healthy adults, Parkinson's disease, multiple sclerosis, chronic obstructive pulmonary disease, congestive heart failure, and proximal femur fracture from different geographical contexts and cultural contexts. To verify the sensor data quality, we developed device testing, and we tested the 72 each single device that were used for the technical validation. We were able in this way also to provide a statistical description of the noise, which allowed to compare the device that we use for Mobilise with other commercial devices available in the market. Algorithm and performance were first tested in the lab under well-known conditions. Data were collected in 5 different clinical centers using as reference standard an optoelectronic stereophotometric system composed by multiple infrared cameras. The experimental protocol was conceived in collaboration with the clinician to be acceptable for all the patients and to allow to capture a broad range and type of gaits reflecting those encountered during real world. To fulfill these requirements, we identified 7 different motor tasks at different velocity, including turning, standing and sitting to a chair, walking on different surface, and obstacles. And in addition, we also consider a motor test aimed at simulating those activities which are usually expected to be performed at home, including interaction with tables, with chairs, and other objects. The second phase of the algorithm validation included 2.5 hours of free living acquisition to test the algorithms under unsupervised and ecological conditions. In this case, we use as a reference standard a multi-sensor system, the INDIP, which included pressure insoles, magneto-inertial measurement unit attached to the feet and to the pelvis, distance sensor attached to the shank. In this way, we could directly measure the gate temporal events and then to estimate the displacement by integrating the acceleration with a very high accuracy. Errors on walking speed mean errors are expected to be below 2%. For the third testing level, subjects were asked to wear a device for 7 days for assessing wearability and acceptability. We adopted previously validated questionnaires alongside with any intervention-specific measures, and the results of the interview showed that the device was easy to use, did not interfere with daily activities, and was comfortable and perceived as useful. We also used a mobile app, iQuora, developed from the group of Professor Ciravegna for identifying other contextual factors based on the information provided by the GPS, Wi-Fi, and OpenStreetMap. And the application was able to provide information whether the person was indoor, outdoor, was walking on the habitual path, or on a slope. Of course, it seems easy, but it's not, as there are several issues that can affect the quality of the final results. Now, the last challenge. We have to process, how to process and to analyze the huge amount of data that we collected. To compare the outcomes provided by the Mobilise single device method against those provided by the reference system, the first step was to match the walking bout. If the same walking bout was identified by both reference and Mobilise method, then we have a true positive. Otherwise, a false positive or a false negative. Based on the walking bout matching, we computed a set of performance metrics, and then for each true walking bout and for each digital mobility outcomes described by a continuous variable, we computed several metrics for criterion validity. This can be done at different aggregation level, at a walking bout level, at subject level, or at cohort level. Okay. We are almost at the end of this 5 years journey. Some results. Results were in general very good across cohorts and condition, and expected the validity of the digital mobility outcomes increase considering walking bout longer than 10 seconds, while decrease for walking bout including having a high gate complexity and characterized by a very low walking speed. It was particularly evident for the stride length and for the speed length, as these two digital mobility outcomes are more sensitive to intermittent gait. Pathology-wise, larger errors were expected were found for the population with the most impaired gait, which was the proximal femur fracture cohort. And you can find full details about the results and single conditions on the papers that has been published and can be found online. To better understand how the Mobilise method works in practice, let's analyze some paradigmatic gait recordings. So in these first experiments, the subject starts walking with a very slow speed, and then he accelerates, as you can also notice from the increase of the amplitude of the acceleration. As you can notice, the very first small strides are missed, but then as soon as the gait speed increases over a given threshold, then the Mobilise computational pipeline is able to detect the changes in gait speed quite accurately. What happens if the subject does not lift the foot while walking? The method proved to be very robust and was still able to detect each initial contact with quite acceptable errors. And during daily life, we all experience that walking can be very complex. There are stairs, turns to stop for opening doors, and sometimes walking can be very fragmented, especially if you forgot your keys. However, as you can see from the graph, in this case we could get a one-to-one matching between corresponding activities detected by the reference system and those detected by the Mobilise method. Of course, the duration can be slightly different, but it was like a very nice result. So, before concluding, I want to remind that one of the primary requirements of the project was that the Mobilise computational pipeline has to be device agnostic, because we want, in the future, that can be used with many different types of devices. Therefore, we also verified and proved the method validity in terms of equivalence to change in electronics, attachment modality, electronics, and attachment modality. From each challenge, we learned something, and here there is a summary of the main results, but I'm not going into detail as R. Müller will now discuss the most important achievement, and I really want to thank all the people involved in the technical validation studies. It was a real team effort, but I think that we really made it. Thank you very much.